right. So, any questions before we get started? Anybody have last minute genetic algorithm questions, especially with the hot topic right now? Are there questions? The question is what? I don't have an answer for you. Are there any questions? I would assume a lot of you have questions about genetic algorithm. If anyone's brave enough to just shout out their question. I mean, if not, yeah. Primary objective. What is it tested for? The primary objective, what is it tested for is the question. The primary objective is testing a fourth application of the genetic algorithm that's hidden from you. One thing I will say about it is it does have 2 genes in it. So it's somewhere in between the polynomials, objectives 1 and 2. So objective 1, you only have 1 gene, 1 dimension. The polynomial, you have to have at least 3. You have to have at least degree 2 polynomials, 3 coefficients, and 3 genes. The primary objective is another application, but it has 2 genes. So if you're doing well on the polynomial and you're very accurate on that, then you should be able to get the primary. So I would expect the primary to come as you're just working through the 3 objectives. Somewhere while you're working on objective 2, somewhere before you get full credit on objective 2, that's when I would expect you to just make a submission and say, oh crap, I got the primary objective points now, cool. But if you just keep going through the 3 objectives, you should get that primary objective along the way. If you have full credit on objectives 1 and 2, and you know that you didn't choose the incorrect solutions, you didn't have something weird going on there where you were able to just sneak by. If you legitimately have objectives 1 and 2 and don't have the primary, I'd be surprised if that'd be something I'd want to see. If you're in that situation, I'd like to take a look at your submission and see what's going on with that. But I'd be surprised if somebody got full credit for objectives 1 and 2, legitimate full credit, without getting the primary. Question? It has to be exactly 7. So the question is, with the velocity having to be 7, would you just throw away a lot of your random genes? This is a question of how you're setting up your genes. So for example, it sounds like you're setting up your genes with 2 genes, 1 for X and 1 for Y. And then if the magnitude of that vector is not equal to 7, you would want to throw it away. Is that kind of what you're doing?
Yeah, as of right now, I guess. I really don't know how else to filter out.
Right, but that's your question. Like, you have this problem. I'm generating random X and Y. Most of the time, it's not going to be magnitude 7. So what do I do? Right? Am I getting the question right? Okay, so this is a question of how do we convert our genes into potential velocities. If you just choose straight up X and Y, one thing you could do is when you get the X and Y, scale it so it does have magnitude 7. This can work. So say you have 2 genes and their values are 1 and 1. You would change those to the square root of 7, whatever that is. You would change those both to the square root of 7, and then have that be in your incubator. Take those X and Y, normalize it, multiply each by 7, and then that's your vector for that set of genes. That's one way of doing it. I'll give a little bit of a hint for this one. My solution for objective 3 only has 1 gene. I turn that into a 1-dimensional problem. So when you're trying to decide what exactly we need to know, like what piece of information do I need to know to figure out where to shoot? We need the X and the Y eventually, but really, if we had just the angle at which we're going to shoot, we could determine, based on knowing the magnitude has to be 7, what the exact x and y would be. It's more of a hint than I wanted to give there, but that's fine. All right, does that help clear that up? But you don't want to throw away genes. If you have a set of genes that's invalid, you should be rethinking how you're setting up your incubator, how you're setting up your genes, and then make some changes along the way so you don't have invalid genes. And as with any machine learning or any AI, anything in this field, there's something called the curse of dimensionality. As your number of dimensions goes up, your accuracy goes down exponentially. So going from 1 dimension to 2 dimension to 3 dimension, each step is a huge step. So going from objective 1 to objective 2, when you're going from 1 dimension to 3, your algorithm is going to be really tested when you get to that degree 3. You have a cubic increase in the amount of solution space that you have to explore with this. Then when you get to the bonus objective, you have many dimensions. You have, I don't even remember how many mine are, but tens of dimensions that you have to go through. Your algorithm has to be really accurate to be able to narrow that down pretty quick. Luckily for the bonus, there's so many legitimate, possible solutions that the solution space is just filled. It's just packed with potential correct answers. So that one was carefully chosen to be not too demanding of your genetic algorithm. But in general, machine learning, the number of dimensions just blows up in a lot of solution spaces. For example, for image processing, the number of dimensions in your input is the number of, typically anyway, the number of pixels in your image. It's a lot of dimensions, it's a lot of stuff you have to guess if you're training it with the genetic algorithm. That's why the methods get a lot more advanced than the genetic algorithm, which is pretty much just guess and check, if you want to study machine learning. Any other questions? Is everyone feeling about genetic algorithm? Feeling good? Gonna finish it tomorrow? Yes. Some no. Sounds like. Okay. All right. Let's get into binary search trees. And just a reminder, in case somebody's completely not paying attention, genetic algorithm is due tomorrow. If you're not aware of that, please start now. There's only about half the remaining class that's even made a submission. So I know a lot of people haven't. Hopefully all of you have submitted. It's just people who aren't in the room that haven't even submitted yet. But it is what it is. I thought by this time of the semester everybody would know to start early on these things, but anyway. So lecture question today, we're going to talk about binary search trees. Your lecture question is to convert a binary search tree into a list in sorted order. Fairly simple statement. The solution can be simple if you're understanding the tree material quite well, but it can be pretty tricky if you don't. So converting BST to a list, same story as last time, 20 points and you get 2 days, which, I don't know, I'm starting to regret the 2 days already too. Looking at the last lecture question, not everybody, but a lot of the class put it off to the last minute and then didn't finish it, because where the deadline is, everyone does it 1 hour before that. Yeah.
When you say it's
We'll talk about that in today's lecture, but it is in order. In the next 2 lecture questions, same thing. For the 2 graph lectures next week, it'll be 20 points and 2 days to do the lecture question. All right, let's get into some BSTs. So what's a BST? A binary search tree. This is going to be a tree with those 2 properties that I kind of briefly mentioned last time. Every element, every left child of every node has a value that's less than that value. So for every node in this tree, its left child has a value that's less than it. And every value of every right child has a value that's greater than its value. These two properties not have to hold, depending on how ties are handled. But these 2 properties roughly have to hold for the binary search tree. And if these properties are true for every single node, then we can call it a binary search tree and say that it has, that it is a binary search tree, I should say. The duplicates, if we have a tie value, this is different based on implementations. For my implementation, I'll put ties to the right. I'm like 90% sure. I'm slipping a little bit on that one, but I'll put ties to the right. It doesn't matter, it's an arbitrary choice. Or some implementations just don't allow ties at all. So for example, if you had a key value store based on a binary search tree, which some of them are based on binary search trees, you just wouldn't allow ties because you don't allow duplicate keys. So if you had a key value store is a BST, your node values would be sorted based on that comparator, and if the comparator says that these two values are equal, just don't allow that, replace the node or whatever, and then the nodes would store the key and the value, but they'd be sorted based on the keys if you were using BST to store a key value store. Or if you want to represent a set, some languages have set data structures. A set mathematically does not allow duplicates, so it's common to use a BST or even a hash table, which we'll talk about next semester, to store those values and remove the duplicates. Make sure you have no duplicate values. So it's kind of arbitrary. It can be different based on implementation how ties are handled, but at least these two properties will be handled with one of them getting the equal to or the equal to just not being in the tree at all. So with that, that is a BST. That's the whole definition. That's what a BST is. That's what they are. Now let's talk about the why and how of that. So binary search tree, we're going to build this off of our tree nodes that we explored last lecture. We're going to take our binary tree nodes, build a tree, and make sure that it maintains that structure of a binary search tree. So to do this, we're going to take in the type that we're storing along with a comparator to be able to tell the order. So in the previous slide, I say less than, greater than. I'm using those common terms. But really, we're using a generic comparator as we've done for the past several weeks. We're going to take a general comparator that can be thought of as a less than function, or rather the less than function is a valid comparator. But it's going to give us a way to be able to compare two values of type A. We're going to initialize the root of our tree as null, and then have two methods. I want to be able to insert values into this tree, and I want to be able to find values that I've inserted into this tree. I want to be able to insert and find, and we'll see simple implementations of both of these that aren't great, and we'll talk about why towards the end of the lecture. And you'll notice that remove is not in here if I want to remove an element. I briefly talked about that on a little tangent in the previous lecture and how we would remove from a binary search tree. I was way off track from traversals from last lecture. But removing from a binary search tree and maintaining those properties gets a little tricky. It's not too overly complicated, but it's a little trickier than we really need to talk about today. So if I have insert and find fully implemented, this is what some usage of our binary search tree would look like. I would give it a comparator. I just want to do the typical in sorted order, so I'll give it the less than function. I'll insert all these values. I want to find 4. I should be able to get this node that was created when I inserted 4 into this binary search tree. So that's what we want. Those are the properties we want. My question is, how are we going to implement these two methods to get all the properties that we want? So find, I'm going to do both of these recursively with trees. The recursion, just like last time, the recursion really helps us out when we're working with trees here. To find, actually, I guess find you could do without recursion, but find, I'm going to call find. I want to find this element and return the node that it belongs to. So I'm going to define a second method that's going to be the recursive version of find. And this is common in a lot of recursive methods. You can't just write one recursive method and have that one be the one that everybody calls. I have this find, which just takes a value A to find. That's how users want to use this method. They don't want any extra parameters there. But in my find helper, I'm going to need a second parameter. So I define this as a whole nother method. So I have another method that's just going to control the recursion of my find method. So my recursive find is going to take the value I want to find and the current node that I'm looking at, that I'm exploring at this moment, and then return whatever we're trying to find. Now if the node we're looking at is null, return null, we didn't find it. If the node we're looking at, its value is less than the value, or greater than, I gotta be careful how I say this. If the comparator of A and this value returns true, which is to say that A should come before the value of this node in the full sorted order, if A has to come before this value, then I'm going to recursively call this on the left subtree. If it's greater than, or rather if this node's value comes before A in the sorted order, then I'm going to the right subtree. And if both of these are false, so if A doesn't come strictly before this value and this value doesn't come strictly before A, following the definition of our comparator, then this node's value must be equivalent to what I'm looking for, so I'm going to return this node. I found what I'm looking for, I'm going to return it. So and this is how we can do equality with just the comparator. So if this is the less than, A is not less than this value, and this value is not less than A, then we're going to say these values are equivalent based on this comparator. They might not be overall equivalent for ints and less than they are, but according to this comparator, their relative order does not matter, so we're going to consider that a match, say they're equivalent, and then I can return this node. So if I have this BST and I want to find the value 4, I'm going to start at the node, or start at the root node. 4 is less than 5, so I'm going to go to the left. 4 is greater than 2, or 2 is less than 4, rather. We only have a less than, we don't have a greater than function, but I'll reverse this. 2 is less than 4, so I'm going to go to the right. And 4 less than 4 is false, and 4 less than 4 is false. Those are the two checks that would be made here in the code. So I'm going to say these values are equivalent. 4 is what I'm looking for, so I'm going to return this node, a reference to this node, up the recursion. Insert, same concept, but a little bit different. If I find, so basically I'm going to run find, and as soon as I find a null value, I'm going to insert the value there. I'm going to insert my new node there. So insert, if the root is null, my root is that, and I'm done. If the root is not null, we're going to jump to the recursive version of this, following the same structure as find, and I'm going to start at the root and insert this value A. So my helper takes that value and it starts at the root, and if this value is less than A, or if this value comes before A in the fully sorted order, and that means we need to be looking to the right. If the right is null, that's where I'm going to place this thing. If right is not null, recursively call this on the right child. Else, A comes either before this value, I do put them to the left, I was wrong earlier. If A comes before this value, or is equivalent, so this is how I'm breaking ties here. So as long as the value doesn't come strictly before A, go over here, which is either they're tied, they're equivalent, or A comes before this value. In either of those cases, I'm going to shove this to the left subtree. If the left child is null, I've already found the place where I'm going to put this new value. Oops. Else, make the recursive call on that left child and keep going over to the left. Or not keep going over to the left, but go to the left and then call this recursively to see where to put it from there. So if I want to insert 7 into this, I compare 7 and 5. 5 comes before 7, so I'm going to the right child. 7 comes before 8, and so this goes to the left, and the left child of this node is null. So we've already found the spot where we want to insert 7 into this BST. We're going to create a new node, set the left child of this node to that new node, and then we're done. We're done with that recursion. We're done with that insertion. Any questions so far? Yes.
Still an analytical one, but does at least the first of the binary tree, does that have the median of the data set?
No, not necessarily. In the example I'm showing currently, it is because I have a fully balanced binary search tree. But a binary search tree does not necessarily have to be balanced, and I will talk about that towards the end in a couple slides here. I'll show the implications of that. But that is a very deep topic. It is, my TAs picked on me because I said this so many times last lecture, but that's a 250 topic. You will learn all about that until you are so sick of hearing about it in 250. You will talk all about balanced binary search trees, how to insert and keep a balanced structure, how to delete and keep a balanced structure, and how to get that as close to possible as of the root being the median. That would be one of the goals. But that's beyond 116 for sure. I'll motivate it, I'll talk about what the problem is, but I'm not going to talk about solutions in this class. Yeah.
How you wrote the insert, so if you were to insert another 14, would it go to the left or the right?
With my implementation, it would go to the left. So if I want to insert 14 again, I would insert that right here. Just the way I wrote my code. But those ties can be broken arbitrarily. If I put that to the right, it would still be a valid binary search tree according to the definition. It's just up to the implementation. It's one thing that's undefined by the actual theoretical binary search tree. So I could either put it in the left, put it in the right, or not allow duplicates at all. Those would be the three options. They're all valid options. I happen to put them to the left, but it's arbitrary. Oh, the slides are here. So we want these trees to be balanced for efficiency purposes. So these are very fast, either both insert and find are fast operations, the way we have them coded, if the tree is balanced. If the tree is balanced, meaning it has the same number of descendants or same size subtrees for its left and right child, if this is true for all the nodes of the tree, or at least if those sizes are only off by a constant factor, then we call this BST balanced. If it's balanced, then we have really nice efficiency in both of these. To go from the root to any leaf, which is what both our algorithms do, it's going from the root, and then in worst case, it's taking the longest branch to the furthest leaf. In both of these, if our BST is balanced, that'll take log n steps. Each time you go down, if you think of this as layers, each layer you go down, you're doubling the number of nodes. So to get to a total number of nodes of n, the total number of nodes in the whole tree, you would have to go down log n layers if you sum that up. It's similar to the reason we get n log n from our merge sort. From our merge sort algorithm, when we looked at the recursion tree of that, that would be a fully balanced, not fully I guess, but a balanced tree, a balanced recursion tree, and that took log n layers to get down to that bottom layer, to that base case, where we had our full thing. It's the same math, very similar math. Each time we go down, we're doubling the number of nodes. It's going to take us log n layers to get down to the end if this is a balanced BST. So if it's balanced, we get log n insert, log n find, and we can implement log n delete that we're not going to do today. And this actually gives us another n log n sort. If we can insert in log n time, take your n values, insert them all into a BST, and you've sorted those values in log n time. And you can do an in-order traversal to be able to visit all those elements in sorted order. We can get that in n log n time with a binary search tree. So we get another method of sorting if we can insert in log n time, which means that we have to be able to insert while maintaining a balanced tree. If I talked about that last time, I don't need to take that. But if the way our the way our insert is written, it really depends on the order in which we insert the values. So what if we do the worst case thing for our implementation is insert values in sorted order? If we insert these in sorted order, we're left with something that strongly resembles a linked list, and we're going to get O of n efficiency on any algorithms we have. Insert is O of n in this case, find O of n, delete O of n no matter what we're doing, because if we have to delete that the very last node, we have to navigate through this entire tree, we have to visit every single element. Everything blows up to O of n, and we have basically a linked list. We have linked list efficiency all around if we do this. So this is very bad. We'd like to avoid this, but the question is, how do we insert in a way that maintains the balanced structure regardless of the values, the order in which we insert these values, even if we insert them in sorted order? And the answer that you'll learn about in 250 AVL trees and red-black trees is to, after each insert, restructure the tree if needed. So once we start inserting these, I believe once you get to the 4 on both those implementations, you would restructure this tree and make the 2 the new root, move 3 to a subtree, move 4 to that right subtree, and keep restructuring the tree. But every restructure has to happen in log n time as well to maintain your efficiency. So that's a 250 topic that may or may not give you nightmares, but it's not too bad, but it's a notorious topic for students. Students do not like going through that one. I didn't like going through it when I learned it either, for what it's worth. So everything's O of n with this implementation, so how do we avoid that? I already talked about all this, but I'll leave the slide up for a second. And back to lecture question. Any questions? Any more questions? We have 20 minutes left, so either me and the TAs will walk around answering questions, or anybody have a question for the whole class? All right. I'll stick around and answer questions. Other than that, I'll see you Friday. Don't forget about genetic algorithm and the quiz on Friday.